Because unfortunately, quantum physics fall under online class. So this is one of the weird topic. It's one of the weird topic which tells a lot of weird things, which later found to be true. Okay, still questionable, but some proven. Okay, through quantum physics. So far, what you learn about under quantum physics? The most devastating experiment for science is a photoelectric effect. Why? Because as I said, the outcome was totally against wave idea, against wave idea for light. What are the three factors against wave idea? The time delay. They should not have. It happens instantaneously, but wave predicted they should have a time delay. Second, any frequency should be emitted according to the wave idea, but found to be there is a cutoff frequency, threshold frequency. Third, the kinetic energy of the electron looks like dependent to frequency and not intensity. But wave idea said intensity, not frequency. Okay, so now we'll under confusion after Einstein got Nobel Prize for this. We'll come to confusion. Is it light? Is it a wave or particle? Definitely it's wave. 99.9%, as I told you, a lot of proof. It diffract, it refract, it reflect, interfere. So it is wave. But sometimes when you interact with matter, it shows another character. So it has a dual character. So wave found to be is wave, but it also has a particle nature. Okay. Then comes in another scientist. After that, he said de Broglie. Is de Broglie. So de Broglie. De Broglie, a French scientist. He said that, not surprising, because he said not wave got particle nature. He said particle as a wave nature. Particle as a wave nature. So what is meant by particle as a wave nature? You see, like electron. Electron is particle or wave. Electron is a particle. You are particle or wave. We are particle, like one single unit. We are particle. Do you have wavelength? Or you have wavelength? Your O levels studies. If they ask, what is the wavelength of Usain Bolt? Something's wrong with the question, right? Okay, now in A levels, after you learn quantum physics, what is the wavelength of Usain Bolt? The students start to calculate. Okay, so human has wavelength according to de Broglie. De Broglie said particle as wavelength. So he said wave particle duality. Wave as a particle nature, particle as a wave nature. Wave as a particle nature. What is the proof? Photoelectric effect. Okay, wave looks like got particle nature. The energy is in terms of packet, photon. Then particle as a wave nature. Yes, according to de Broglie, there is one. He said electron diffraction pattern. Electron shows diffraction pattern. Electron is a particle and pass through a small graphite carbon solid in front. The graphite atom spacing is atom spacing close to the size of electron, so electrons start to deviate. It shows us diffraction pattern. Okay, if let's say electron, like a particle, pass through a small gap. Electron is a particle. We expected the electron to move in a straight line and hit one single point, and the fluorescence screen must change the kinetic energy to light, and the light must be a one bright spot at the center only when the electron comes up. But what they observe is a fringe. Okay, they saw a fringe. This is a fringe. The electron only hits here. Only hits here. The electron does not hit here. So it forms a fringe. Diffraction pattern. Diffraction is only done by a wave, not a particle. Okay? The particle shows diffraction pattern. The particle has a wave nature. Okay? This is the only proof, de Broglie evidence. So based on this, de Broglie said, okay, you see wave as a particle nature, particle as a wave nature. It shows electron diffract. So particle shows wave nature. So he come up with a very controversial formula. This is the formula, lambda equals to H over P. Very controversial. Controversial because see the formula. On the left side is what? Wavelength. Wavelength linked to another quantity P. P is what? Momentum. Lambda equals to H over P. Okay, this lambda called wavelength. Why is it so weird? You see, wavelength belongs to wave. Wave as wavelength. But this formula tells a certain wavelength can have a certain amount of momentum. Okay, like light. You shine a light to the dog, and dog experience a force. Shine a light. O-level studies, early studies. Okay, light as a momentum. Light don't have momentum. It's a wave. Okay, but according to him, a wave lambda can have a momentum. Okay, an electron which has a momentum P, now it can associate with certain amount of wavelength. Okay, the proof in de Broglie is more to momentum to wavelength, particle giving wavelength. Okay, that's the de Broglie evidence law. More to momentum to wavelength. Okay, so if an electron has a momentum of P, then how much is the wavelength associated to the electron? The lambda equals to H over P. Okay, very controversial. Yeah, H is a Planck constant. Planck constant, godfather of this idea. Okay, so lambda equals to H over P. If the momentum gets smaller, what happens to the wavelength? Wavelength increases. When wavelength increases, you're going to diffract more or diffract less? More diffraction. Become more diffraction. And momentum reduce, wavelength increases, more diffracted. Okay. So yeah, this is the formula you have to remember. Okay, lambda equals to H over P. So moving electron displays a diffraction pattern. Particle exhibits wave property. Okay, this is the proof for what? Particle as a wave nature. Okay, particle as a wave nature. So wave as a particle nature, particle as a wave nature. That's what done by de Broglie. Okay, so you have wave character and wave as particle character. Okay, so now if they ask, if a person is walking, he has a wavelength. When he's running, what happened to his wavelength? Increases or decreases? When he runs, momentum increases, so wavelength get smaller. Okay, so wavelength gets smaller. This wavelength they call de Broglie wavelength. It's called de Broglie wavelength. They won't just mention wavelength. It's a de Broglie wavelength. Okay, now tell me, what happened to this diffraction pattern? What happened to this diffraction pattern when the speed of the electron is increased? When the speed of the electron is increased, the electron was increased speed. We use a very high voltage. Now this diagram uses 4,000 volt. We use 6,000 volt. Let's say the speed has been increased. What happened to the diffraction pattern? The fringe get closer or further? The fringe get closer. Why? Less diffracted or more diffracted? When momentum increases, wavelength become shorter. Lambda equals to H over P. When momentum increases, because speed increases, momentum increases, wavelength gets smaller, So less diffracted. Less diffract means the fringe get closer. The fringe will get closer. Okay. So can't show the diffraction pattern. Okay. In exam they ask what happened when the speed is increased. The fringe get closer. And there is 1 year they asked if the electron assumed to be particle, what is expected on the screen? They never conducted the experiment. Before they moved the electron, directed the electron to the plate, the graphite as the plate. What they should expect it if it's a particle, just a bright dot at the center, uniform distribution they call it, a bright dot. Like let's say, like you have a small gap, you throw a tennis ball from a firing gun, let's say tennis ball, 1,000 tennis ball was launched maybe in 30 seconds, let's say. So fire the tennis ball along a gap which comparable size with the tennis ball. If the tennis ball diameter, let's say, is 5 centimeter, the gap like maybe 6 centimeter around. He passes the tennis ball, because the tennis ball is a particle or wave. Tennis ball is a particle, it's non-unit, it's a particle. It's exactly the same as electron, you know. Electron also moving a gap of graphite, it shows the diffraction pattern. Okay, so they try with the tennis ball. They said if the tennis ball is a particle with a particular wavelength, it also should follow this formula. If the wavelength is quite big for the tennis ball also, when it come out from the slit, it should hit only at a specific points. It show the diffraction pattern. It should show the diffraction pattern. Okay, you can't hit. There is a region where you never hit at all. You show the diffraction pattern. Okay, like human walking out from this door, like we all walking out from this door. Okay, without using your brain, just move up. Okay, according to them, at a high speed, let's say at a low speed, your momentum must be very small so that you have a big wavelength. When you come out from the door, like closing eyes, just past the door. Like according to what they are trying to say is, let's say there is a wall there, there's a carbon paper on the wall, let's say where you go and hit the wall. So if 20 of you come out from the door, according to them, you as a particle must have a wave nature. You must show a diffraction pattern. It means maybe 3 or 4 of you hit the center, the other side, maybe go to the side, you diffract, weird. When you walk, you will be diffracted. Okay, and there will be a region where you won't collide at all. There is a center region, like it's a fringe pattern, like fringe pattern will be experienced by a particle if the wavelength is quite significant. Okay, but so far they never seen even tennis ball show that diffraction pattern. Only happens in electron. Okay, why electron? Because the momentum is so small until the wavelength is quite significant, quite big, show the diffraction pattern. Okay, so this is the diffraction pattern by using a light wave, but now electron shows a diffraction pattern. So now question is going to be about wavelengths. All the particles has wavelengths. Okay, first question. Find the de Broglie wavelength for 10-gram bullet traveling at a speed of 300 meters per second. So this is the de Broglie wavelength. Okay, so whenever I say de Broglie wavelength, lambda equals to h over p must come to your mind. So just find the momentum, h over p, the momentum, you get the wavelength. Electron traveling with a speed of 6 times 10 power 6. A proton accelerated through a potential difference of 100 volt. Out of A, B, C, which one do you think will have a greatest wavelength? A will have the greatest wavelength. Lambda equals to h over p. The smallest momentum will have the greatest wavelength. Which has the smallest momentum? A, B, C. Subatomic particle, right? Because its mass is going to be very small, although it travels so fast. A, I don't think so will have the smallest momentum. Bullet with 10 gram with the 300, I think it has although speed is quite small, but mass is quite big, 10 gram. Okay, so I go to the next page because it's just calculating the momentum. Okay. So which one will have the largest wavelength? So yeah, electron. electron, 1.2 times 10 power negative 10. So the bullet, even though it's as a 300 meter per second, quite slow compared to the other, but its mass is 10 gram, quite huge. Its wavelength still quite small. Okay. So bullet traveling, I think its wavelength associated with is too small. So it can't show the diffraction pattern. It can't show the wave property. Okay, so that's the idea of quantum physics here. You have wave property. Your wavelength is too small for you to show the diffraction, to show the interference. Very weird. Yeah, so that's what has been developed in science so far. Okay. Okay, any question about de Broglie? So de Broglie, his PhD thesis, he wrote this and he got a Nobel Prize for that. Thesis, PhD. Particle is an electron, yeah. The electron has wave property. The electron create the, it shows a wave property, like wave diffract, right? Electron particle also shows diffraction pattern. It has wave property.
Yeah, but for light, right, the particle is photons and the wave is light.
Okay.
And for electron, the particle is electron, then what is wave?
Okay, light is a wave. Okay, but we consider light as a wave. Okay, when interact with matter, it looks like the energy was in form of particle. It's a two, what do you call, it's a two characters together. Two characters together. Okay, it's not like you can differentiate. Okay, wave is wave, light is a wave. You see, photon is a particle. Photon is a concept brought into the wave. It's in the packet, they give the name for it as a photon. But for electron, no two names. So electron as a particle shows a wave property. It shows diffraction. Okay. Okay. So until now, we don't see any significant contribution of quantum physics. Okay. Actual contribution of quantum physics we want to see is a laser. Okay, laser is a contribution of quantum physics. Laser is a very useful component for us, our daily life, right? Laser. Okay. Your CD read by laser. Okay. Lots of treatment and everything. Laser. Okay, laser was developed in the quantum physics, and the next development was your atomic structure. Who developed atomic structure? The first scientist is what? Dalton. After that is what? Thomas. J.J. Thomas. Then after that, Rutherford. What Rutherford said? Nucleus at the center surrounded by electron. Okay. After Rutherford, the model is not settled. Came who? Chadwick. Chadwick and Niels Bohr. Niels Bohr and Chadwick. Niels Bohr. Okay. So we are talking about Niels Bohr. Okay. So the Rutherford model got one problem. Okay. Rutherford says what? According to Rutherford 1911, he said through alpha particle scattering, electron evolves at a high speed in a circular orbit around a positively charged nucleus. This is what we learned. Okay. But there is a drawback in this idea. The drawback is, according to classical electromagnetic theory, if any charged particle, you never learned this yet, any charged particle, if it accelerates, like electron proton, if it accelerates, you give out radiation. The energy will be changed to radiation, according to Maxwell. Okay, according to Maxwell, another scientist, too many scientists. Okay, so any charged particle accelerate, we give out radiation. Radiation means it produces EM radiation. That means from where the energy was, it got EM radiation from its kinetic energy. Okay, when it accelerate, it give out EM radiation. Results to going to consequence is what? The charged particle will start to slow down. It releases the energy. So according to Rutherford experiment, his model, what is the drawback is, according to classical electromagnetic theory, a charged particle will accelerate around another charged particle, then there would be a continuous radiation of energy. Energy would be radiated as EM radiation. Okay. So therefore, if electron move around in a circular path, you learn in under circular motion, anything move in a circular path, do it accelerate? It accelerates towards the center, right? The centripetal acceleration. So it accelerates. So when it accelerates, the electron should loses energy. So because electron loses energy, what happened to the electron? He slowly must get close to the nucleus. Okay. The loss of energy would slow down the speed of electron. Eventually, the electron would fall into the nucleus. But that doesn't happen. Okay, electrons just keep on move around the nucleus without falling down. Although it accelerating, it give out radiation, but it doesn't slows down. It never fall to the nucleus. So the model of Rutherford got problem. The problem is not about the nucleus. The problem about the electron movement. Okay. So later, Niels Bohr explained this problem. Niels Bohr used his quantum physics. He said, Niels Bohr said he applies a quantum theory, used a derivation by using quantum theory. Never show here. He proposed that electron travels in a stationary orbit, or the electron has a fixed orbit. Okay, the electron can't move like randomly like a squirrel and get into the center. It has a fixed orbit. Okay, like a track. It cannot come out from the track. Okay, it has a fixed orbit like this: orbit 1, orbit 2, and orbit 3. Okay, it can't have electron cannot move in between it. It only can have a fixed orbit, according to him. And this led to the calculation of possible energy levels. He say different orbit has a different energy levels. Okay, so he postulated that the emission of light occurs when the electron moves into the lower energy orbit. Okay, so this is the idea. Niels Bohr said what? Electron has a fixed orbit. Okay, how he got it? From quantum theory. See, all of them are theoretical physics. They can tell whatever story they like, but need to have proof. Okay, so he said, according to quantum derivation, the electron has energies, subspecific energies. Okay, so then he said, according to him, he said, okay, the electron can move only in a certain allowed orbits around the nucleus. Okay, so this is the derivation. I skip this. I go to this first. Okay, so this is the energy levels. So the lowest energy level, the nucleus is down here. You can imagine the nucleus is here, down here. The closest energy level to the nucleus is N1. We call ground state. The lowest energy level electron can stay, and this is the second energy level electron can stay. These are the energy levels. And the energy levels, according to the quantum derivation, they found that the energy levels get closer and closer and closer. Okay, according to the derivation. It is proportional to 1 over r squared, if I'm not mistaken, the distance. So when you go further, the energy levels are quite a lot, but quite close by. Okay, so according to Niels Bohr, say the free electron will be at infinite, at zero potential energy. Okay, free electron will be at infinite. They are at infinite. They are free. Okay, so at zero potential energy, they have zero potential energy. All energy levels are negative. Why all negative energy levels are negative? Like gravity. Do you have potential, positive potential or negative potential? You have negative potential. Why you have negative potential? Because your potential caused by an attractive force, right? If any potential caused by an attractive force, that potential is considered negative. The nucleus is positive, the electron is negative, it's an attractive force. The potential possessed by the electron is negative. Okay, so that's why all energy levels are negative. Okay, indicating the loss of potential energy nearer to the nucleus. So the energy levels N1 as the lowest potential energy, ground state, we call it ground state. And the ground state for hydrogen is negative 13.6 E. You need to remember, what you need to know is the ground state will have the highest negative potential energy. And go higher, the potential energy become less negative. You see, negative 13.6 become negative 3.39. Same thing as your gravity one. Now you have highest negative potential energy. When you climb mountain, what happens? Your potential energy become less negative, right? You go to infinite, your gravitational potential energy become zero. Same concept. Okay. Okay. So now this another. So the electron, according to him, is not going to stay at the same point. Normally, he said like at low energy level, like the atoms in these bricks, and everything. The smallest unit is atom. So inside atom got electron. The electron, when it's very cold, the situation is very cold, low energy. All electron, according to Niels is at the ground state. They will be at the ground state. They will be at the lower state. Okay, they will at the lower state, lower energy level. Okay, but when suddenly, okay, so when suddenly the electron given energy, how electron can receive energy? When you on the light, when you on the light or heat transmitted to the wall atom receive energy, the electron receive energy. What happened to the electron? You jump to the high energy level. Okay, go to the high energy level. So the electron will go to high energy level as shown here. The arrows are like transition of electron. Let's say this level is negative 13 point, I put a round number. Let's say this is negative 10. This is negative, let's say 6, negative 10 EV, negative 6 EV. There is a number. Okay, so negative 10 EV, negative 6 EV. If an electron get a photon of 4 EV, the electron will jump to the second energy level. Okay, if it receives a photon of 4 EV, the light gives the 4 EV of photon, it absorbs, it go to second energy level. Okay, let's say the energy here, let's say is negative 5 EV. Okay, if the electron receive how many EV, jump to negative 5, negative 10 to negative 5. So 5 EV of photon reach, you go to this energy level, the third energy level. Okay, so if the electron got, let's say, energy of 4.5 EV, 4.5 EV, it won't take that photon. Okay, it's very particular, according to the theory. So it's very particular. Let's say the electron receive 4.5 EV, 4 EV enough to jump to the second level, right? But it's 4.5 EV. It can go first level, but it can't go to the second level, intermediate. It seems you won't absorb this photon. You only take either 4 or 5, no intermediate. Exact amount you absorb. Okay, according to Niels Bohr. Okay, his theory. So electron very specific. You only take the specific photon, just nice for the energy transfer. Okay, so the ground state has negative 13.6 EV. Let's say negative 13.6. If the electron receives negative 13.6 EV, it totally escapes from the atom. Okay, become free electron. This is the idea. Okay, so now and now light is on. Prediction is all electron in this wall, the atoms, the electrons are in an excited state. They already went to the high energy level now. All are in high energy level. Prediction. Okay, and after finish class, when you shut down the light and in the night become cold, all electron will go down to the ground state. They lose energy and release gas spirit. So if it absorbs the light photon, when it comes down, it should releases the light back. Okay, it releases the light back. Okay, it give out the light back. If it absorbs light photon, okay, the only substance I think absorbing light photon is your fluorescent. Your watch fluorescent, and the dark. When you bright, all the electron are going to the higher state. Okay, when go to the dark room, what happened? The electron fall back, releases the same light that absorbs. Okay, so it give out light. Okay, but never happened for this wall. Maybe this wall atom, the energy level is not in the visible light range. Okay, maybe in a UV range, maybe. So when UV absorb, when UV is exposed, you go to that state. Okay, then later when the cold and come down, it releases UV, which we can't see. Okay, but according to scientists, you see every moment the electron are going up and come down, going up absorbs energy, coming down releases the energy again. If it's a visible range, it will give light. Now it happens for fluorescent substance only. Okay, other substance they do that, but radiation is coming out but not visible. We don't know what range they are emitting. Is it in a radio frequency or in a UV? We don't know. It depends on the energy level in the atom. Okay. Okay, so this is the first one here. This is called absorption spectrum. This is emission spectrum. Okay, absorption means electron absorbs energy, goes up. Absorption spectrum. Okay, when it goes down, emission spectrum. Emission means what? It goes down and emit photon. Emission spectrum. Okay. So a lot of wording, but I straight go to the point. You see, so the lower energy level, negative 10 EV, another energy level, let's say negative 6 EV. To go up from here to here, the photon energy required is the HF form, is in a photon. So HF must be same as high energy minus the low energy. So this is the formula you need to remember. That's what I explained here. I already told you, electron move up, absorbs energy, move down, emit the photon. Okay. Okay. So let's understand this concept, the Boss concept. Okay, one question. Okay, this is hydrogen atoms energy level 13.6, 3.4, and so on. Okay, what is the ionization energy of the hydrogen atom? So of course, negative 13.6 EV is the ionization energy. Okay, the ground state energy is the ionization energy. Okay, you give that much of energy, the electron totally will be released, the atom become ionized. Okay. Okay, next, what is the minimum frequency of the photon that is required to cause an electron to ground state of the hydrogen atom to be ionized? Oh, so what is the minimum frequency required? So the energy of the photon must be 13.6 EV. So what is the frequency? So how do you do that? The 13.6 EV must be equal to what? HF. HF, so you find the frequency. The EV change to joule. You have to change to joule. Change to joule, you do what? Multiply by 1.6 times 10 power negative 19. So joule, then HF, you get the frequency. That's your B answer. Okay, the minimum frequency. Okay. C. What would be likely to happen to photon of energy 12.7 EV and 15 EV if they pass through gaseous hydrogen atoms in the ground state? You now check the values. Tell me, two photons are exposed to the electron, 12.7 EV and 15 EV. Which one will be absorbed by the electron? Can you take 15 EV? 15 is 13.6, so you won't take 15. So you will take 12.75. If it absorbs 12.75, exactly can jump to which level? E2, E3, E4? 4. From here, it jump to here. Electron jump to here. Right? 13.6 minus 0.85, you get 12.75. So the electron, it absorbs 12.75 EV, straight it jump to the fourth level. Okay, it stays there for a while, excited state. Okay. Okay, so 15 EV won't absorb because you need 13.6 exactly. Okay, now D. Okay. Okay, D I haven't told you yet. Okay, D. Look at the question first. Try to understand. Bombarding electron of energy of 5 EV and 11 EV collide with gaseous hydrogen atom in the ground state. What they are trying to say. Okay, they say the hydrogen atom, this is the hydrogen atom. Another electron was fired into the hydrogen atom, which carries an energy of 5 EV and 11 EV, was sent into the hydrogen atom so that it collides with the initial electron. It collides with the electron which is in the orbit. So how much energy is absorbed by the gaseous hydrogen atom electron in the ground state? This outer electron, you know, this electron is alien actually. It's come out from, we are sending it to the hydrogen atom, go and collide. This electron has a 5 EV and 11 EV. Okay, so how much of the initial electron will absorb? Due to collision, the electron tend to receive some energy. So how much of energy is going to take? Can you take 5 EV, 11 EV? Okay, this is collision. If collision means it take the amount of energy required for the electron. Okay, not like photon. Photon either you take it or you totally don't want that photon. But during collision, you can take the sufficient energy required to jump. Okay, so you don't need to take all the 5 eV. You don't need to take all the 11 eV. What is the energy required to jump the first step? 13.6 minus 10 something, right? 10.2. So you take from 11 eV, you take the 10.2 eV something, you jump to here. The electron in the orbit will jump to the E2, okay, by absorbing 10.2 eV, right? 13.6 minus 3.4, 10.2. Okay, so you take 10.2 from that incoming electron, and what happened? The incoming electron will come out again with how much of energy? The rest of the 0.8 eV. It will come out with 0.8 eV. Okay, so this is the difference between photon and collision. During collision, you can take whatever amount of energy from the electron to jump. Okay, can it take 5 eV? It will take any energy from 5 eV. You won't take any single energy from 5 eV because not possible to jump even first step. So the 5 eV electron go and collide. It come out also with 5 eV. The electron just will come out with 5 eV. Okay, so this is the theory behind. They say this is what happening. Okay. Okay, next, the last one. If hydrogen atom is in the energy level of N3, the hydrogen atom is in the N3. Okay, N3, show all the possible transition that can undergo on the diagram and find the corresponding frequency of the photons. Okay, what is the question? What they are trying to say? The electron is currently at E3. Okay, let me show this. Okay, let's say you have 4 energy levels. The electron is here. Okay, the electron is here. When the electron comes down, when it comes down, there are many different ways it can come down. Like you can imagine the electron like a ball at here falling down. Okay, the ball is falling down. So these all are like, you can imagine like energy levels. These all are like energy levels. So the ball can hit here and comes down. So, or you can hit at the second one and it comes down. So there are many options. Hit here and comes down. So many different options you can come down, right? Same things for electron. What are the options the electron can come down? You can reach here, or you can straight go down. Or after the electron come to this stage, electron can come down. So this electron can give how many types of frequencies? 3 different type of photons will be released. Okay. So let's say you have 4 energy level. If the electron is at the top here, how many types of photon will be released? Top here. So you try to draw from the top here. 1, then to the second level, 2, then third level, 3. Okay, then the electron here, after you jump here, you can have 1 and 2 here. Then from this level, you can have another 1. So from the first stage, you can have how many type of photon can be released? 6 photons can be released. In exam, they will ask you to draw this pattern. Okay. Normally they go for 3, 4 very rare, but they can ask. Okay. So from the level where it is, draw one after another. The first one, the second one, and the last one. Okay. Then they go to the next level, first one and the second one. So these are 6 different type of photon will be released from that metal. Okay. But tell me, which photon has the highest frequency? Which has the lowest frequency? So which has the highest frequency? 1, 2, 3, 4, 5, 6. Which one has the highest frequency? Of course, the 3. The HF, the third one. The third one has the highest frequency, the maximum. Which has the lowest frequency? Which has the lowest frequency? 1. 1 has the lowest frequency. HF1 is the lowest frequency. Minimum. Next time I ask this. Okay. Highest frequency, the greatest transition of energy level. The smallest frequency is the smallest energy level transition. Sometimes they will trick you. They'll ask, which gives you the greatest wavelength? Which transition gives the greatest wavelength of the photon? 1, the other way around, right? 1 greatest wavelength. The 3 is the shortest wavelength. Okay. Okay, this is the transition of electron. The type of transition I'm showing you, absorption spectrum or emission spectrum. It emit photon, absorb photon. Goes down, it emit photon. So emission spectrum, call it emission spectrum. Because sometimes they'll ask you an exam, draw the emission spectrum of the electron. So you should know, should go down, emit photon. Sometimes they ask you draw absorption spectrum. Absorption means you have to make the electron to go up, going up. Okay, so we go back to the question. So the E. Okay, for the E, the hydrogen atom in the energy level N3 show all the possible transition. So we can draw now, right? So it is at N3. So what you're supposed to draw is 1 and 2 and the third one. Okay. So undergo on diagram on the find corresponding frequency of the photon emitted absorbed during the transition. Okay, so these are the answers. This is the transition you should draw. This you can draw here. It's the same. Okay. These are the answers we discussed. Okay. Okay. So very nice story by Niels Bohr. But is it true or false? If there is a proof, yes, there is a proof for it. And the proof for Niels Bohr is the line spectra. Line spectra is proving this idea. And he got a Nobel Prize after that. Everyone got a Nobel Prize. So Niels Bohr, whatever quantum idea is said, quantum idea is like one imaginary storyline of quantum physics. Finally, you're talking about the atomic electron energy level through derivation. And later, when they do the experiment, the outcome was matching with this theory. Okay, that's why we can't deny quantum physics. Okay, quantum physics proving something which is not solved before. Okay, the energy level. So what is meant by line spectra proving the Niels Bohr's idea? Okay, this is the emission spectrum, and the lower one is absorption spectrum. Emission spectrum, electron going where? From up to down. The absorption spectrum is electron going from down to up. Okay. So what is emission spectrum? What the setup they use? It is the setup they use. This is a setup to prove emission spectrum. Emission spectrum means electron should go from up to down. Okay, you see the setup. The first they use a heated gas at low pressure. Heated gas. Why they use heated gas? Heated gas means the gas is very hot, so all electrons got lots of energy. So what happened to the electron? They will be at a ground state or the excited state? Theoretically, they all must be in an excited state. Okay, you want to prove Niels Bohr wrong, right? So it should be in an excited state, like according to Niels Bohr. Okay, so all excited state imaginary. That hot gas was lived for a while. They put a lens here and they put a prism here. Okay, so let's say when the electron goes down, it give out photon. Okay, a photon, and the photon is a wave go and hit the prism, and it was refracted and shine to a photographic plate. The photographic plate change color. Okay, change color. This photographic plate, the lowest we know is violet. The above going to be red. Okay, so according to emission spectrum, is what they observe. What they observe, a background is dark because they done it in the dark room. Okay, dark room because they want the light only comes out from the gas, the hot gas. Okay, photographic plate is very sensitive. dark room. We don't want any light to hit the photography to change color. Any light comes out should be from the gas, heated gas. So the heated gas show these lines. How many lines are there? 1, 2, 3, 4, 5. 5 lines, let's say. But these are specific wavelengths. These are specific wavelengths. We can calculate the wavelengths. These are the specific wavelengths. So we can get the energy of this. This is actually what? It's characteristic of the electron transition. The electron goes down, give out photon. That photon energy is what? HCO lambda. This wavelength is actually wavelength we get from this formula, right? Okay. So this line is a photon release characteristic of what? Characteristic of the energy level, right? The energy level. Electron, let's say you got negative 10 eV of energy level, here negative 13 eV. So when it goes down, it gives a photon of 3 eV. The wavelength here it shows must be character of that 3 eV, correct? Okay, so if Niels Bohr is correct, then the absorption spectrum must prove whether it's correct or wrong. Because absorption spectrum is what? The electron will move up, So what they do, the absorption spectrum, they did like this. This is the heated gas. This absorption spectrum setup. Absorption spectrum, they use what type of gas? They use a cool gas. So it means what? All electron at the ground state. Then what they do? They shine the gas with a white light. Incandescent light, a white light. 7 wavelengths was transmitted to the gas. So the electron must take the wavelength required, right? So you take the wavelength required, and the electron will be excited here. Then what happened? This light is supposed to be what? A spectrum, right? A wavelength spectrum. When the color reach here, some light will be missing, correct? The light missing because of what? The electron absorbs the light to go up. The light it missing must be the one appeared earlier, right? Because same energy level one. So they did the experiment. They found that the one appeared here is the one disappeared here. Okay, the same wavelength has been disappeared. So this proves that electron has certain amount of energy level. The same energy has been absorbed, has been released. Okay, so this proof Niels Bohr is correct. So worth giving him a Nobel Prize for that. 1 million US maybe, I think. Okay. So yeah, so 1924, I think he discovered this. So this is our today's lesson. Okay. So Niels Bohr said electron got lots of energy level. What is the proof? Line spectra. They will ask, line spectra got 2 types, emission spectrum and absorption spectrum. Next time they will ask how emission spectrum looks like, how absorption left spectrum looks like. Emission spectrum is continuous color line with a dark background. This 2 marks question. They will ask how the appearance looks like. Emission line spectra is background is dark with color lines. Absorption spectrum with the dark lines with colored background. Okay, this is the absorption spectrum. Even one wave, if not the same line with the above, Niels Bohr is wrong. Okay, it's found to be exactly the same. Okay, so what you learned today? Learn about all weird things. De Broglie wavelength, very weird. What we De Broglie said, wave particle duality. Wave has a particle nature, particle has a wave nature. What is the proof wave has a particle nature? Photoelectric effect. What is the proof that particle has a wave nature? Electron diffraction pattern. Okay, so we have wave nature and wave has a particle nature. Okay, last class seniors, when I teach this lesson, the first time photoelectric effect, end of the class I ask them, what do you learn from photoelectric effect? They say light is not a wave. It's wrong. Light is both. Light is wave, but it has a particle character. Don't say light is not a wave. Light is wave, but it has a particle character. Okay. Okay, now you learn particle as a wave character. Okay, only proven for subatomic particle. So stop here.